Hello everyone. The title of this video is Using the Definition of a Logarithm to Solve Logarithmic Equations. So in this video, I'm going to be doing examples that are taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 6.6 called Exponential and Logarithmic Equations, and I'm under the heading Using the Definition of a Logarithm to Solve Logarithmic Equations. And each example I'm going to do in this video is going to be either one of the examples from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Alright, so remember the definition of a logarithm here. They have it written out right here. Hopefully you recall from earlier videos as well how to transfer back and forth between logarithmic form and exponential form. That's going to be key. I'll write that up here before we get into our first example. So remember, if I have a logarithmic statement, the log base b of, and I'll write it the way they're writing it, of s equals c. All right, there's a statement in logarithmic form. Remember, this is equivalent to the following statement that b to the c power equals s. And this is exponential form here, right? So this is going to be key. Being able to go from logarithmic form to exponential form. And then, of course, solve the resulting equation and check your solutions back in the original equation. Alright, so for every single one of these problems today, I have an equation with a logarithm in it, and I would like to first write it like this, where I have a logarithm by itself on one side of the equation, and then some number on the other side. So in my first example, I'm solving 2 times the natural log of x, remember that's the log base e, plus 3 equals 7. So I would first like to get this natural log of x alone, isolate that. Alright, isolate that. Alright, so first I would be subtracting 3 from both sides. So we have 2 times the natural log of x equals 7 minus 3 is 4. Then divide both sides by 2. We have the natural log of x equals 2. So there's a nice statement in logarithmic form, right? I have a logarithm base e of x equals 2. And then we change to exponential form, right? Now I'm just going to put exp form. And the equivalent exponential form would be x equals e to the second power. Or e to the second power equals x. Same thing, but I just wanted the variable on the left side. And then you solve this equation here, which it already is solved for. There's our solution. X equals e squared. All right, e squared. Now, of course, they would call this the exact answer, right, before I punch it in a calculator and then round it. Now, in some exercises, you might be asked to round to the nearest, like, thousandth or 10,000th or whatever. I'm going to round all my answers here to the nearest thousandth. So the calculator I like going to, right, is the free online graphing calculator at desmos.com. And I'm going to punch in a value, and I'm going to call this value little a when I use it in other calculations. And a equals, e squared, right? Our solution is e squared, and e squared looks like about 7.389. 7.389. So back on my paper, I've already written this, right? That's the rounded answer, right? The approximate answer. And of course, let's check this. Plug this back in here. Now, if you plug in e squared, it's pretty easy. The natural log of e squared would just be 2, and then 2 times 2 is 4, plus 3 is 7. Right, this totally works. Or you could use your calculator even. That's why I called it a or some letter. Just call call my solution some letter. I called it a, and then I plug it in for x. So the left side of that equation was 2 times the natural log of x. So I'm replacing x with a, and then you got plus 3 on the left side, and you see how that's equal to 7, right? The other side. So that totally works. That is a totally valid solution. Great. Alright, and I'm going to be doing pretty much the same thing for the rest of this video. Alright, so example 2. Got 6 plus the natural log of x equals 10. Once again, I would like to isolate that logarithm just by subtracting 6. So we have the natural log of x equals, 10 minus 6 is 4. Then I change this to the equivalent exponential form. And that would be e to the 4th power equals x, or x equals e to the 4th power. And there you go. X equals e to the 4th. And if I were to plug in e to the 4th power, right, the natural log of e to the 4th power would be 4, and 6 plus 4 is 10. This works. And of course, that's called, again, the exact answer. If I want to get a roundabout answer, right, an approximate answer, I'll just go back here. What's e to the 4th power? Well, that's 54.598 if I round to the nearest thousandth. 54.598. And then again, I have it called a here. So if we punch that into our equation, the left side was 6 plus the natural log of x. So 6 plus the natural log of a, you see it's equal to 10, which was the right side. You get 10 equals 10. So that totally works. Alright, so example 3. Same kind of idea here. Gotta get this logarithm, this natural log of x plus 1. I want to isolate this. And the only way to do that would be to divide by this 2. So I divide by 2. Got the natural log of x plus 1 equals 5. And now I have a logarithmic statement. We change it to the equivalent exponential form. I'll just put exp for exponential form. And that would be x plus 1 equals e to the 5th power. Now this is not solved for yet. Right? I still have to get x alone by subtracting 1. So x equals whatever e to the 5th power is, and then minus 1 after that. And there you go. And let me round this also to 3 decimal places. So back here, e to the 5th power, and then minus 1. Right? So the value of our solution is approximately 147.413. And I'm just writing that on my paper. I know you can't see it, but. And then if we test it out, the left side of the equation was 2 times the natural log of x plus 1, but I'm replacing x with what I called a plus 1, and you see it's equal to 10, which was the right side. So, totally good solution there. Excellent. Alright, similar concept for the rest of them. So number 4. Once again, I have a logarithm, but this time it's a logarithm base 9, right? Not base e anymore. But I still want to get that alone first, get a nice logarithmic statement, log equals. So I'm going to divide by negative 8. So now we have the log base 9 of x equals, 16 divided by negative 8 is negative 2. And now I have a logarithmic statement. We change it to the equivalent exponential form. That's x equals 9 to the negative second. 9 to the negative 2 power. But remember what 9 to the negative 2 power is. That's just 1 over 81, 1 over 9 squared. And here we go. There's our solution. 1/81st, 1 over 9 squared. And let me once again test this out. Why not? Right, so back here again, I'm going to call this thing I plug into the equation A in the calculator. 1 over 81 is this number, 0.012345679, no 8 there. And then we have negative 8 times the log base 9 of A, and you see it's equal to 16. Right, the right side was 16. And I plugged A into the left side. It makes it true. 16 equals 16. Wonderful. All right, very similar here. Only this time the logarithm is base 10. All right, remember when there's no base on the log, it's base 10, a common logarithm. But still, I would like to isolate this. So you would subtract 6 and get 4 over here, and then divide by 2 to get 2 on the other side. So we have the log base 10 of 8n plus 4 equals 2 after isolating the logarithm. Right, subtracting 6, then dividing by 2. Now I have a logarithmic statement. I change to the equivalent exponential form. And this would be 8n plus 4 equals 10 to the second power, which is 100. Now I haven't solved for n yet. All right, first I need to subtract 4. 8n equals 96, and then divide by 8, so n equals 12. Right, there's our solution. 12. And if you were to plug that in, 8 times 12 is 96, plus 4 is 100, the log of 100 is 2, times 2 is 4, plus 6 is 10, this works. Right? And again, you can use the calculator to check if you wish as well. All right. This next example, pretty simple to start. It's already set up as a logarithmic statement, right? I got the log by itself. It's not being multiplied by anything. There's nothing added to it, subtracted from it. It's not being divided by anything. And it's equal to a number. The log of something equals a number. So I can start right away by changing this to the equivalent exponential form. So 7x plus 6 must be equal to 2 to the third power. But 2 to the third power is 8. Then I subtract 6. We have 7x equals 2. And then divide by 7, and we get our solution. X equals 2/7. And then go ahead and check it, right? If you plug in 2/7 for x, this would be 2 plus 6. This is 8. The log base 2 of 8 is 3. That is true. Okay. All right. So again, all pretty much the same. All these problems are worked out the same way. So here I'm going to isolate this log base 3 of x. I want the logarithm alone. So first I subtract 3. So now we have the log base 3 of x equals, 2 minus 3 is -1. Now I have a logarithmic statement. Change to the equivalent exponential form. So x would be equal to 3 to the -1 power. But remember, 3 to the -1 is just 1 over 3 to the 1. It's 1/3. So our solution is 1/3. And that works. You plug that in. The log base 3 of a third is -1, and -1 plus 3 is 2. So that's good. Great. I just got one more page. Again, I'm doing the same thing every time, getting the logarithm alone, and then changing to exponential form and solving, and of course checking your solution with either a calculator or by hand. Now example 8, it's already set up the way I want. The logarithm is alone. The log base e natural log of x minus 5 equals a number, 1. So I'm going to change this to the equivalent exponential form. So x minus 5, right, must be equal to e to the first power, or just e. And then I would just add 5. So x equals, e plus 5. And there's our solution. All right. And again, if you punch this in and round it, you can, into a calculator, check it. If you plug in e plus 5 here, you'd get the natural log of e equals 1. That works. Right. So e plus 5. Use the calculator to round it if you're asked to. And then I have just one final example here. Again, I'm doing the same stuff. So first I would like to isolate this logarithm base 3 of 4 minus x. So this -7, I'm going to add 7 to both sides. Right, so now we have the log base 3 of 4 minus x equals, -6 plus 7 is 1. Alright, now I have a logarithmic statement. I'm going to change to the equivalent exponential statement. So this would be 4 minus x equals 3 to the first power, which is just 3. So clearly x must be equal to 1. And there's your solution. And if you were to plug 1 in, 4 minus 1 is 3. The log base 3 of 3 is 1. And -7 plus 1 is -6. Right, so this works. Great. Alright, so these were all equations with a term that had a single log. Right, there was a single logarithm in the equation. You isolate that log, change to exponential form, and solve the resulting equation. And then, of course, you should be checking your solution back in the original equation when you're finished, just to make sure. Great. And that's it. So I'm hoping that watching me go through these 9 examples here help you in some way when you're trying to use the definition of a logarithm to solve logarithmic equations on your own. And thank you very much for watching.